Hello, good afternoon. Welcome to the stream. We are back with Essentials of Compilation. Today we are going to be looking at garbage collection, which is a problem that lots of languages have to deal with. So our language that we're building is a Lisp-like language, and Lisp, of course, is known for list processing. We don't have lists in our language yet, but it is an essential part of how the language operates. And so today, last time we implemented vectors. So vectors are fixed length collections of heterogeneous types, and we made it possible to express those in our language and also type check and interpret them. So that was interesting. And today we need to look at, well, what do we do with these? In order for vectors, as they're called in Racket, in order for vectors to exist, they have to be placed somewhere. All of our values so far have fit into registers or into single slots on the stack. But vectors do not. Vectors are multiple words wide. And they may contain other vectors. So essentially we have the introduction of pointers, at least in the implementation, if not in the semantics. So we have to deal with the fact that we may have a value which does not fit on the stack, and so instead we put a pointer to that thing, either on the stack or in a register. And then when we need things out of that structure, we follow that pointer and index into the space that follows the end of that pointer to get the values out that we care about. And depending on what the contents of that structure is, we may have to follow multiple pointers. So all this to say, we've been just using the stack and registers, but now we will be putting things on the heap. And putting things on the heap means that there's no like return, at which point we can, pop the stack and basically invalidate all the contents of that space that was previously allocated when we called into a function. We don't have that with the heap. Those things may live for an indefinite amount of time. Effectively, they say, effectively to the programmer, tuples live forever, or vectors in this case they're calling it. So we need to make sure that we can reclaim the space allocated to those data structures when they are no longer reachable, so when they're no longer needed. A lot of different languages have different approaches. Of course, dynamic languages like Gleam, JavaScript, Erlang, so forth, they rely on the runtime system to do garbage collection. They don't implement it themselves. So, and then there's what was I going to say? And then there's languages like C, where you're, into some respects, C++, where you are responsible for allocating and deallocating memory. So when you need something to be on the heap, you call malloc, and malloc will give you a pointer to the space that you can put that data in. But then you are also responsible for later freeing that memory. So if you are no longer using it, you have to manually release it. Otherwise, you essentially have a memory leak. And then another method is reference counting, which is supposedly a dual of garbage collection, but it's basically like every time you acquire a pointer to an object, and a count is a counter is incremented on that object. So when I say object, I don't mean object as an object oriented programming. I mean object as in a block of memory on the heap that refers to some data structure that you're concerned about. So reference counting is every time you create a pointer to that object, you increment its counter. Every time a pointer to that object gets freed or falls out of scope, you decrement the counter. Whereas a garbage collection is like so okay, let me finish up reference counting. Reference counting, when that counter gets to 0, that object can be freed. And that happens automatically by the mechanisms of the language. Garbage collection says, well, I'm not going to track everything because you may have circular references and so forth, and those can be difficult to free if you don't know, because those reference counts will never go to 0 if they're circular in some sense. So you have to make sure that that there's a way to reclaim that memory. Well, garbage collection says, well, I only care about what's reachable. So I'm going to look at what's reachable from the program. That is, what has references to it on the stack or in registers. And then I'll keep track of those things, and those are called the roots. And then I can follow the roots and find all of the other objects on the heap that are still live. And now, while this is an over approximation of whether something can be or has to be retained, it is a correct approximation. So it will never throw away something that actually might be in use. However, sometimes it'll keep around some things that might no longer be in use. So that's the strategy of garbage collection: is look at all the things that are reachable, follow all the edges, the pointers to other things that are reachable, and anything that isn't in that set can be reclaimed. Okay, so then there's the secret third way, which is Rust's way, which is that things are explicitly consumed is one way to look at it. So you have methods like close on file or build on a builder object, which consumes that object. So that object is moved into that method and can no longer be accessed after that method is finished. So it has an idea of references. References can be given out freely, and as long as the original thing is not moved, references can be created. But once something is moved, either it falls out of scope or it's explicitly handed to something that takes ownership, then that thing can be freed. So that's the secret third way. But the most common are manual memory management, like we talked about in C, garbage collection, reference counting. So our language is going to use garbage collection. And let's have a look at what we got in the book. So we ended around here. 6.2 talks about garbage collection. So it says garbage collection is a runtime technique for reclaiming space on the heap that will not be used in the future of the running program. So that's essentially what we're trying to do. We're trying to make sure that nothing that we have hanging around is no longer in use. So again, I explained this a moment ago, but they say we use the term object to refer to any value that is stored on the heap, which for now includes only tuples. So again, they over-approximate the set of objects that will be accessed by identifying which objects can be possibly accessed. So again, even if something is, say, about to fall out of scope and will no longer be used, you have to keep it around because something might have a reference to it. We're not tracking references. We're only tracking the existence of something on the stack. Existence of a pointer, excuse me. So the running program can directly access objects that are in registers on the procedure call stack, and also transitively access the elements of tuples, starting with a tuple whose address is in a register or on the stack. Okay, so that is the definition of the root set. So all the addresses that are in registers are on the call stack. The live objects are the objects that are reachable from that root set. So garbage collectors reclaim space that is allocated to objects that are no longer live. So they are not reachable from that root set, basically. Okay, and again, this is sound. It's not complete, it's not perfect, but it's sound because it doesn't reclaim space of things that might be live in the future. So then, this is an important point. The programmer can influence which objects get reclaimed by causing them to be unreachable. Okay, so that means you can return from a function that had some temporary values on the stack. Once the stack gets popped back to the original position, anything deeper on the stack, higher on the stack from the point where it was popped to, is basically invalid, and so it's not reachable. Okay, so those are ways that you can influence what the garbage collector does. So the goal of the garbage collector is twofold: to preserve all the live objects and to reclaim the memory of everything else that is garbage. So the algorithm that they're going to introduce to us here is a two-space copying collector. It is a variant of the mark and sweep, I believe. But essentially, the idea is that when you find an object that is live, you have the heap partitioned into two areas. So you have the current generation and the next generation. And in this one, it's when you find a live object, you copy the entire thing over into the other heap, the other partition of the heap, and you follow all of the things it points to and copy them all to the heap. And then when you've found all the live objects, then this generation becomes the next generation, so everything in there is considered invalid, and you've copied everything over into this other space for the live objects. So you don't have to explicitly deallocate things in that first partition, but you do have to copy. So there are performance impacts on that for sure, but essentially you don't have to worry about explicitly freeing all of the things that are unreachable. You just consider that whole memory space to be invalid. Okay, so let's read a little bit more. In particular, so there are variants on this. This is a two-space copying collector. Other kinds of copying collectors include the generational garbage collectors. So things that have lived a long time, gradually, on each run of the collection, they gradually get moved into an older space, and so you don't. The idea there is that in a lot of programs there are very few things that stay around a long time, and then depending on how many generations you want to keep around, the stuff that is done in the regular the regular operation of your program is likely going to be very short-lived objects, and so those get reclaimed more often. And so they're in a young generation. If they survive one, they get copied to, either the old generation or some kind of like middle-aged generation. And then you don't have to traverse the older generations as often in order to reclaim space. You basically go look at what are all the young objects first. I'm going to prioritize cleaning those up because I know that they're likely going to be thrown away versus the stuff that's older. Now this one, it's just a full heap copy as far as I understand it. Okay. So let's, they're listing off all of the authors about related to garbage collection. Okay, so they're going to describe a two-space copying collector. It uses Cheney's algorithm to perform the copy, so we'll have to read about what that is. Figure 6.5 gives a coarse-grained description of what happens in a two-space collector. We'll scroll down to that in a minute. Okay, so 2 time steps, prior to garbage collection and after garbage collection on the bottom. In a two-space collector, the heap is divided into 2 parts, namely the from space and the to space. So essentially, you have a pointer to the from space and a pointer to the to space. You do the copies into the to space, and then you swap the pointers, and that's what the garbage collection is. So all allocations go to the from space until there's not enough room. At that point, the garbage collector goes to work to make room for the next allocation. Okay. A copying collector makes more room by copying all the live objects from the from space into the to space, and then performs a sleight of hand, treating the to space as the new from space, and so forth. That's why I was talking about swapping pointers to the heaps. Okay. In figure 6.5, the root set consists of 3 pointers, 1 in a register and 2 on the stack. All the live objects have been copied to the to space in a way that preserves the pointer relationships. So, in other words, if you have a vector inside a vector, you have to copy, and it's probably like a depth first situation. You have to copy and update any pointers that are contained inside other vectors. So that's kind of interesting bit of algorithm there. And it's pretty straightforward to express recursively, so I think we'll be fine. Okay. For example, the pointer in the register still points to a tuple that in turn points to 2 other tuples. So there are 4 tuples that are not reachable from the root set and therefore do not get copied into the to space. So they're warning that the figure in 6.5 cannot be created by a well-typed program in our language because it contains a cycle. However, creating cycles will be possible once we get to L-dyne. We designed the garbage collector to deal with cycles to begin with, so we will not need to revisit this issue. Okay, so let's jump down to this figure. Okay, so this is the before and this is the after. Okay, so in the registers we have, any number of values, one of which is a pointer, and it points to a tuple of 2 elements. Okay. Again, this has cycles, so it's going to be a little bit confusing. So that's one root right there. And then on the stack, you have a pointer that points to this, so that's another root. And you'll notice that this is actually probably what happened is they accessed the first element of this tuple and they got that, and that went on the stack. Excuse me. Okay, and then there's one more thing on the stack, and it points to this tuple, which points to a tuple that has 1 element in it, and then its second element is a number. You will see that if we follow the transitivity of these pointers, we have all of these elements. Again, this has cycles. All these elements are reachable in this top group here. This group is reachable, but this group and this group are not reachable. I guess this is technically not a cycle, but it is a little bit suspect. Okay, so if we were just to walk through this manually, we might go, okay, this tuple needs to be copied, this tuple needs to be copied, this tuple needs to be copied, this tuple needs to be copied. Let's go down here. Okay, this one has already been copied, and so we can just move on, and then we need to copy this tuple and this tuple. So You can see that in the after here. What has happened is all these things in the heap have been copied to this space, and then the pointers in the register and on the stack have been updated to point to the new locations of those objects. Okay, so let's look at the next section. So let's take a closer look at the copying of the live objects. The allocated objects and pointers can be viewed as a graph, and we need to copy the part of the graph that is reachable from the root set. So that we just kind of like did our little thought experiment walking through that. To make sure that we copy all the reachable vertices in the graph, we need an exhaustive graph traversal algorithm, such as depth first search or breadth first. Recall that such algorithms take into account the possibility of cycles by marking which vertices have already been visited. So it's assured termination of the algorithm. So there will probably be some data structure where we track the pointers, I guess. So like the addresses of tuples, such that we don't have to visit them again. So they use a stack or a queue as a to-do list to keep track of the ones that need to be visited. Okay, they say we use breadth first search and a trick due to Cheney for simultaneously representing the queue and copying tuples into the to space. Okay, so then they're talking about figure 6.6. It shows several snapshots of the two spaces the copy progresses. So this is going to be a little bit hard. So the queue is represented by a chunk of contiguous memory at the beginning of the to space, using two pointers to track the front and the back of the queue, called the free pointer and the scan pointer, respectively. Excuse me. The algorithm starts by copying all tuples that are immediately reachable from the root set into the to space to form the initial queue. Okay, so right, so this is okay. I get it now. So if we look at this this diagram, it's going what does this point to? Copy that. What does this point to? Copy that, and they're contiguous. And what does this point to? Copy that. So they copy a tuple, mark the old tuple to indicate that it has been visited. So we're going to see how that marking is accomplished. Note that any pointers inside the copied tuple still point back to the from space, right? So that's what these arrows to the right are talking about, or to the left rather. So, you know, this being the first tuple, it's pointing back into the from space still. We've copied the roots, but we haven't updated any of those pointers. Okay, so here the scan pointer is at the beginning of the heap. And the free pointer is at the end of all the tuples that they've copied. Okay, so then they're going to scan this tuple and go, okay, what did this point to? It pointed to this tuple that we copied here. Now, exactly how they figure that out, I'm not sure. That'll be interesting to know what that data structure looks like. So this pointer gets updated, and then this other pointer, it points to a tuple that we haven't copied yet. So it's copied beyond the free pointer, and we increment the free pointer to the end of the space that was consumed. And then this pointer is updated to that newly allocated tuple. So now the scan pointer has moved forward, and the free pointer is still at the end. Okay, and then it's going to scan this tuple. And in the previous step, this was still pointing back into the from space. So we know that this points to something that we need to copy. So we copy that tuple, we update the pointer, and then the scan pointer advances to the end of this one. And then we do the same with the next one. This puts, you know, that one element tuple at the end, updates the pointer, scan pointer moves to here. This contains no references, so the scan pointer can just move forward. And then finally, this tuple, this element points back to the tuple before it, so it gets updated. And then the scan pointer is here, and the free pointer is there, and then you scan, say, and when the scan pointer equals the free pointer, then you're done. Okay, so that's what they're saying about combining the queue of things to do with the space that you're copying into. That's what they're talking about. Okay. So, right. Copy a tuple, mark the old tuple to indicate that it has been visited. So that's a separate data structure that we're going to have, and I suspect that it's some kind of mapping between the old location and the new location. And that's how it could get updated. You could look up, what does this point to? And if it hasn't been copied yet, then you copy it. If it has been copied, then you just update the reference. Okay. Right, so once the initial queue has been created, the algorithm enters a loop in which it repeatedly processes the tuple at the front of the queue and pops it off the queue. To process a tuple, the algorithm copies all the objects that are directly reachable from it into the to space, placing them at the back of the queue. The algorithm then updates the pointers in the pop tuple so that they point to the newly copied objects. Okay. So, as shown in figure 6.6, the first step, we copy the tuple whose second element is 42 to the back of the queue. That's what they're talking about there. The other pointer goes to a tuple that has already been copied, so we need to copy it again, but we do need to update the pointer. Okay, so this can be accomplished by storing a forwarding pointer to the new location in the old tuple when we initially copied the tuple into the to space. We're going to have to see what they mean by forwarding pointer. I was thinking of like some kind of mapping. But we'll see what they mean there. This completes one step. Okay, and then you continue. That is when the scan pointer catches up with the free pointer. Okay, so the garbage collector places some requirements on the data representations used by our compiler. So this is where we get into the nitty-gritty of what do these tuples actually look like in memory. So first, the garbage collector needs to distinguish between pointers and other kinds of data such as integers. Right. So like the processor doesn't know any difference between a number, a Boolean, a void value, or a pointer. It doesn't know. So what we can do is attach a tag to each object that identifies what type of object it is. That's one possibility. So either using the high or the low bits of the value, which is like a 64-bit word, right? We can determine what kind of thing it is. And this is especially useful for pointer types because you can, because of the requirements of alignment, some of the low bits of a word are not usable as pointers. Like you can only point at whatever the alignment of the processor is. I think it's typically, the word alignment. So you can only point at 64 bits. You can't index within those 64 bits when accessing memory. It has to do with the width of the address bus to memory. But essentially, you can't index at the byte level, for instance. So since 64 bits is 8 bytes, your how we do that? 64 is 2 to the 8th, right? So your bottom 8 bits. Am I getting that right? No, that's too many. That would be 256. So your bottom 6. Yeah, your bottom 6 bits uh, are basically zeros when you're trying to access a space in memory. So that means you can use those 6 bits to describe what that thing is, and that's the technique in option 1. So it says, when I know that this is, for example, a number or a Boolean, I will pick various bits in those bottom 6 bits to represent that type. If it like points to a vector, maybe I'll use the 3rd bit, and then you build up this way of tagging all of your items and all of your values, and there's some bit shifting involved when there's numeric values. But the goal there is that if it's a pointer to something, you can mask off those bottom bits because they're not used when addressing the thing, and then you can use that value as a pointer. Okay, that was a really long-winded way of describing step 1. Okay, the other, and this kind of feels like the slab allocator strategy, which is you store different types of objects in different regions. But the slab allocator is much later than Guy Steele's 1977 paper. Okay, so we can use type information from the program to either generate type-specific code for collecting or generate tables that guide the collector. So this is Appel from 1989, Goldberg 91, and so forth. So dynamically typed language such as Racket need to tag objects in any case. So option 1 is a natural choice for this language. However, LTUP is a statically typed language, so it'd be unfortunate to require tags on every object, especially for small and pervasive objects like integers and booleans. Option 3 is the best performing choice for statically typed languages, but comes with a relatively high implementation complexity. To keep this chapter within a reasonable scope of complexity, we recommend a combination of options 1 and 2, using separate strategies for the stack and the heap. So, regarding the stack, we recommend using a separate stack for pointers, which we call the root stack, aka a shadow stack. So that's interesting. So we're going to make another space in memory that is not really the stack. We'll probably keep a pointer to this stack in a register. It probably won't be the stack pointer register, but we'll see. Okay, so that is when a local variable needs to be spilled and its type is of type vector, we put it on the root stack instead of putting it on the procedure call stack. Furthermore, we always spill tuple type variables if they are live during a call to the collector. So they're saying spill, I think they mean to the procedure call stack? No, they would spill to the root stack. Okay. Thereby ensuring that there are no pointers and registers during a collection, right? Because you have to use those registers during a collection. They're not safe. You'd have to preserve them. And we probably will have a bit where we preserve them. I guess the call into the collector, which is not going to be implemented in our language or in Gleam, honestly. It's probably going to be in C, and note I have it over here on the other side of this. But we need to make sure that the registers are available to the garbage collection algorithm. So they need to be pushed onto the stack when we call into garbage collection, and oops, can I go back to where it was? Okay, shadow stack. And then the garbage collection algorithm can use whatever registers it needs to, and then it'll restore them at the end by popping the stack. Okay. So figure 6.7 reproduces the example in figure 6.5 and contrasts it with the data layout using a root stack. The root stack contains the 2 pointers from the regular stack and also the pointer in the second register. Okay, so let's look at 6.7. Interesting, it jumps to the caption and not the figure, but okay. So, here there's, that pointer that was in a register is now on the root stack. And there's only discrete values on the stack, and that root stack points into the heap. Okay, so that facilitates garbage collection. You don't have to examine anything on the stack or in the registers. You can choose to look at only these things. Okay. The root stack contains a two-pointer. Okay. So the problem of distinguishing between pointers and other kinds of data also arises inside each tuple on the heap. We solve this problem by attaching a tag, an extra 64 bits to each tuple. That's interesting. So they're not tagging the values themselves, which is the McCarthy method. They're tagging the tuple. So, okay, 6.8 shows a view and view of the tags for the two of the tuples in the example given to 6.5. So they've drawn the bits in big endian way from right to left with bit location 0 on the far right, which corresponds to the direction. But even though we're working on a little endian machine, you still kind of represent in a big endian way, just for like ease of understanding for folks who are from the West and read left to right. Okay. Okay, so this corresponds to the direction of the x86 shifting instructions, SALQ, shift left, and SARQ, shift right. Part of the tag is dedicated to specifying which elements of the tuple are pointers, the part labeled pointer mask. Within this pointer mask, a 1 bit indicates there is a pointer, a 0 bit indicates some other kind of data. And the pointer mask starts at bit location 7. So we limit tuples to a maximum size of 50 elements. So we need 50 bits for the pointer mask. The tag also contains two other pieces of information: the length of the tuple, so the number of elements, which here they 1, 2, 3, 4, 5, 6. They have 6 bits, which means yeah, that's plenty. That's 64, but they're only allowing 50 bits for the pointer mask, so 64 is more than sufficient. The tag also contains, okay, so the length of the tuple, the number of elements there. Finally, the bit at location 0 indicates whether the tuple has yet to be copied to the 2 space. Okay, so they're basically like, hey, I've already been copied. If the bit has value 1, then this tuple has not yet been copied. If the bit has value 0, then the entire tag is a forwarding pointer. So the lower 3 bits of a pointer are always 0 in any case, because our tuples are 8-byte aligned. Okay, so our yeah, 8-byte, yeah, 3 bits. Okay. So yeah, and I got that wrong earlier. It's not 6 bits. It's 3 bits, because you index bytes in memory, not bits in memory. Okay, so what did they say about forwarding pointers? Where did we see that? Okay, so that's saying when this bottom bit is 0, the meaning of this tag is completely changed. The pointer mask and the vector length are no longer relevant. It's the entire value here is the location of the new thing. Does everyone follow that? Okay, so if it's 0, then it's a pointer to where the tuple moved to. If it's a 1, then it has not yet been copied. Okay. Those feel like, oh, those aren't actually different states, or rather they're not mutually exclusive states, but in this case for the garbage collector they are. So this when this tag is copied to the new space, it's ORed with all ones. Well, not all ones. It's this bottom bit is set to 1, and then it's already over here, and the original it's set to 0 with the rest of it being the new address, or rather just overwrite it with the new address. Okay, that makes sense to me. When I first read this, that was hard to understand, but now I think I get it. You know, the length, they're limiting to 50 elements max, so 64 is enough to represent that. And then you can just, if you want to get the length, you bit shift and mask to know how long is this vector. And then the pointer mask is the contents of this thing a pointer, and that's for each element. There's 1 bit. Okay, so finally get to the implementation. So this is what I have over here on the right. An implementation of the copy and collector is provided in the runtime.c file. So this is the interface. It says void initialize. So that's going to set up the 2-space copying collector. Void collect is going to take a pointer to the root stack. And again, these are pointers to pointers. So this int64t is the tag of the tuple. And then bytes requested. So this is like, give me some more memory. If the heap is out of memory, then it's going to cause a collection. Okay, and then there's a free pointer, which is probably where's the next spot in the heap that can be allocated to. The from space begin and from space end. So those are kind of like, am I in the from space or am I in the to space? And then the root stack begin, that's the bottom, I guess, or the top of the stack of roots. Okay. So, right. The initialize function creates the from space, to space, and root stack, and should be called in the prelude of the main function. So we will be we'll be calling this function with you know, at the beginning. Okay, the arguments of initialize are the root stack size and the heap size. Both need to be multiples of 64. They're saying 16384 is a good choice for both. So that's, you know, 16K. The initialize function puts the address from the beginning, puts the address of the beginning of the front space into the global free pointer. Okay, so it's going to probably call malloc, right? To get some the heap, right? And then it's going to put that into the global free pointer. Okay, so the free pointer, the global variable from space end points to the address is 1 past the last element of the free space. So that'll be like the free pointer plus whatever the size is. We use half open intervals to represent chunks of memory. So includes this one, not exceeding this other pointer. The root stack begin variable points to the first element of the root stack. Okay, as long as there's room left in the from space, your generated code can allocate tuples simply by moving free pointer forward. Okay, so that's a very, very straightforward allocator. The amount of room left in the from space is the difference between from space end and free pointer. Makes sense. The collect function should be called when there is not enough room left in the from space for the next allocation. Okay, so free pointer is really close to from space end, and we need, say, 6 bytes, and we can't get it. then we start garbage collection. The collect function should be called when there's not enough room left in the from space for the next allocation. The collect function takes a pointer to the current top of the root stack, so one past the last item that was pushed, and the number of bytes that need to be allocated. The collect function performs the copying collection and leaves the heap in a state such that there is enough room for the next allocation. Okay. The introduction of garbage collection has a non-trivial impact on our compiler passes. We introduce a new compiler pass called expose allocation that elaborates the code for allocating tuples. So we will need to do that. We also make significant changes to select instructions, build interference, allocate registers, and prelude inclusion. Make minor changes in several more passes. Okay. The following program serves as our running example. It creates two tuples, one nested inside the other. Both tuples have length 1. The program accesses the element in the inner tuple. So we create a vector which contains a vector which contains 42. And then we deref that vector, getting element 0, so that gives us back this. And then we deref that vector, getting element 0, which, surprise, like every example in this book, returns 42. Okay, so this is a motivating example. And I think that what we're going to have to do at some point is copy in this runtime.c. And we may do a read-through of this, right? Because we'll want to see how that's implemented. Okay, the pass expose allocation lowers tuple creation into making a conditional call to the collector, followed by allocating the appropriate amount of memory and initializing it. So you do expose allocation before remove complex operands because it generates code that it contains complex operands. Okay, so our first thing to do here, we are going to make a new pass, which is called expose allocation. Is that right? Yep. Okay. Rename. Okay. Length L tup as L. Okay. So, okay, so we choose to explain or to place the before remove complex operands. However, with some care, it can also be placed after remove complex operands, which would simplify tuple creation by removing the need to assign the initializing expressions to temporary variables. I don't know if they're going to do that. It says C below. The output of expose allocation is a language calledlalloc that replaces tuple creation with new lower level forms that we use in translation of tuple creation. So we're gonna have to create, and let's just duplicate this. And this is gonna be lalloc. Okay, and then we're going to have to do import eoc langs lalloc as A. I know that's probably not great. Let's do LA. Okay, and then we're going to have expose allocation is going to be a pass, right? And the input is going to be L program, and the output is going to be LA program. Okay, and we'll put a do in there for now. Okay. So they're adding the expressions collect, allocate, and global value. During the instruction selection, the collect n form will become a call to the collect function in runtime.c. The allocate n type form obtains memory for n elements and space at the front for the 64-bit tag. The elements are not initialized. The type parameter is the type of the tuple. Vector type 1, where type I is the... Okay, so interestingly, this allocate takes a type, not something else. So this may be a bit where we have to use our type checker to attach the types to nodes in the language, which we haven't had to do before. Okay. The global value name form reads the value of a global value variable such as free pointer. Okay. So the type information that you need for allocate n type can be obtained by running the type check immediately before the expose allocation pass. This version of the type checker places a special AST node of the form has type around each tuple creation. Okay, so the concrete syntax of has type is has type. Okay, so it looks like you do has type, and then this vector, this is the instantiation of the vector, and then it's just a wrapper around that. So semantically, this is still create this vector, but now we have the type wrapped around it. Okay. The following shows the transformation of tuple creation into a sequence of temporary variable bindings for the initializing expressions, a conditional call to collect, a call to allocate, and the initialization of the tuple. The length placeholder refers to the length of the tuple, and bytes is the total number of bytes that need to be allocated for the tuple, which is 8 for the tag plus length times 8. The sequencing of the initializing expressions E0 to E n minus 1 prior to the allocate is important because they may trigger garbage collection. We cannot have allocated but an uninitialized tuple on the heap during the collection. Okay, I don't completely understand that yet, but let's read through this. So if we have this has type vector E0 through En minus 1, and then the type, we go, and that type is going to be used for building the tag, right? So yeah, okay. So basically, yeah, they're binding each of these expressions. That's what they're talking about. So each of those expressions is bound to a temporary variable. And then they do a let, ignoring the result, and an if the global value of free pointer plus bytes is less than the global value from space end, then don't do anything. So here's where that void, we've never actually used that void directly. And then otherwise collect bytes. Okay. And then so that's creating, or that's checking whether there is enough space. If there isn't, then it calls collect. So this collect has to happen before we allocate. Okay, then the next one, the v, which is the vector, is so this allocate is going to return a pointer, right? Essentially a vector in the semantics, but this is in the implementation. This is a pointer of length, and here's the type, and that type will inform the tag of how to be constructed. And then finally, it's just going to do a bunch of lets that set the values of those elements of the vector. So this is kind of an expensive transformation, right? I don't think that I would expect anything different. This is the mechanics of how it works. But it does introduce a lot of noise into the intermediate passes. So that's interesting. So there's going to be a bit of code generation here where we do kind of like a maybe some continuation passing like we did in some of the explicate control passes and so forth. Okay. Right, again, so they're talking about binding those to temporary variables so that if there's an allocation inside these expressions, then that gets spilled out into this form as well. So if say like E0 is a vector, then you have this entire thing for E0, but it's inside here, and you may collect, you may have to call into the garbage collector for expression 0 before you allocate this vector. Okay, so this kind of has, a turtles all the way down problem. All right, so this is what they're saying will happen from that original one. And the output of the expose allocation pass. So this is, originally we had vector ref, vector ref, vector, vector, 42, 0, 0. Okay. So they're saying this becomes vector ref, vector ref. There's a let. So vec init 6, and then this is a temporary variable that's ignored. This again is a temporary variable. They used x in their example up here, but down here they're saying vec init. Okay, so its first thing is it's going to be binding the inner vector. I wish there were a way for me to keep these both on screen, but so it's binding this one. Okay, so, or no, maybe this is the original. Let's read through. My bad. Okay. Right. Okay. So this is are there 16 bytes? We need 8 bytes for the 42. We need 8 bytes for the tag. Otherwise, try to collect 16 bytes, and then allocate a vector of length 1 with the which the type is vector containing a single integer. Okay, so that's alloc2, so that's the output of allocate, and then it's saying on that resulting vector, call vector set element 0 to 42, and then return that vector. Okay, so now that's bound to vec init 6. And then here's another anonymous one. If there's 16 bytes that can be allocated, we'll do it. Otherwise, we'll try to collect 16 bytes. And then they'll allocate a vector of 1, size 1, where the type is a vector containing a vector of an integer. Okay? And then they set element 0 of that allocated vector to the original vector that we allocated that had one element, which is an integer 42. And then return that. Okay, so now you have this vector that we allocated is returned from this let expression, and then we call vector ref 0 on it, which reads and gets the inner vector, And we call vector ref 0 on that, which reads that vector and gets 42. Okay, so that's expose allocation, what it should produce. Oh, whew. We're an hour in, and I'm already tired of talking. So maybe we should write some code here. We need to add an expression to add an expression to, I think, ltup, or maybe it's lalloc. There's a question in my mind about whether this is we just handle vector nodes by extracting the type, and then we pass that out into this expansion. So if we look here, I think we might need to, and we have type check expression, right? The problem is if this vector, we can't take this vector on its own. So I think that this is where what we'll do in the first language is when we type check, remember we had this possibility of returning a new expression if we needed to transform it. Well, this is a case where we need to transform it. So we're going to add an expression, which is this has type. Okay, so let's make has type, and we'll say value is an expression, and type is type. Yeah, it doesn't like that. We'll say t. Okay, and then when we, so in terms of interpreting this expression, all we have to do is call interpret expression value env, because this is just not used in interpreting. However, in type checking, let's add this pattern here. In type checking, I think that what we do is we don't modify this. What we need to do is when we get a vector declaration, then we wrap it with this has type. Okay, so what we're going to do here is we're going to return, oh shoot, where'd it go? So this is going to return the whole expression, but its value is t. And this is actually just okay. So we're not going to, this means we have already validated that this value, which will be a vector in our case, maybe in future chapters it'll become something else, but we've already validated that this has this type. I don't know that this is actually reachable, but it seems like a reasonable thing to do here. Okay, so the problem is we need a special case, a primitive operation that contains vector. Okay, so we're going to do because vector is not a top level expression, it's a primitive operator. We have to yes, we're going to do this, right? We're going to say a vector E, right? So this is going to return the primitive operator. And then what we're going to return around it is has type. Value is going to be prim vector or prim op, because that's the updated one. And then the type is going to be T. And this is going to be, and then we return type T. So this allows us to wrap that vector with the has type thing. So this will replace all of these declarations with that wrapper, and then we can use this in the later pass in the expose allocation. Okay, so that's step one, I think. And then we don't have to modify this code. It just returns, the type checked operator, and then, the vector T, which has the contents there. Okay. So now we've copiedlalloc. We don't need, let's see, what do we, the problem here is we don't have the has type, so let's copy that over. And in fact, why don't I just delete that and we'll recopy now that we've updated ltup. Duplicate lalloc. Okay. So it's going to have all of the same constructs as ltup, but it's going to add a few. And I think that we don't. We have the types. What we don't need in this step are the interpreter, although that might be interesting. And we don't need the type checker because we've done the type checking. So I think that rounds it out. I think that's, oops. I think that's all she wrote. Yep. Okay, so yeah, we don't need any of these yet. So now we can add these expressions. So we have collect, which has an amount, which is an int. We have allocate, which has an amount, which is an int, and a t, which is a type. And and global value, which is a name, which is string. Okay, so those are the new expressions that this phase is going to inject. Okay. I think we need to look back at this type check lvec has type bit. The problem, I think that we handled it okay. I just want to make sure that that's the strategy that they want us to follow. Yeah. I don't, yeah, I think that this, yeah, I don't think that our strategy is out of line. So let's get to the expose allocation. Okay, so this is going to take the input program and produce the output program. Okay, so we're going to do input body, and we're going to pass that to we're going to say expose expr. Okay, and this can be called recursively, and this is going to be l.e or expression, and this is going to produce an la.expression. Okay, and then we're going to do the typical match. So let's make all the patterns here. So we will need to do the interesting thing here, though, is that with this transformation, this vector primitive goes away, which is really interesting. So that is no longer a primitive operation, because what we turn it into is allocate vector set, and so forth, right? Okay, so I'm going to comment that out. That primitive operation goes away in expose allocation. Interesting. Okay, so let's push, it needs to be early though. let's do and any of these other values that don't contain a primitive vector operation, I think that we need to panic here. Unexpected type wrapper. Okay, because we don't expect that to occur here. We only care about this stuff, right? Okay. So this is okay, so basically this is a very straightforward transformation. This one is also straightforward. These are the exceptional things that we will deal with in a minute. The only one we need to be careful about is this. Yeah, it's okay. Now, one thing that we could do is that we could do the type check here. It feels a little bit weird to do it right before we're trying to determine allocations and not at the head. Like, we should be not trying to compile if the type check fails. So I don't know how I feel about that. It's okay. We'll assume that this has the wrappers around it already when it comes into expose allocation. And there's also possibility that we can do some things in other passes before we get to this one. So, okay. So I'm going to move, I know this was alphabetical. I want the primitive values, or like the really simple ones up here at the top. Like the immediates. You know, this is int. This is var. We're just copying things. Is there not a void operator here? Did we copy ltup from lwhile? Oh, it's a primitive operation. Okay. Okay. And then our if, say let condition is expose expression condition, let if true, and we're just gonna this is going to be la.if, and this is just again another straightforward translation. Okay, and we'll do a similar thing here with let. Okay, so this is actually just a string, so we don't need to do that. I don't know why I thought that the var was going to be an expression. So we're going to make here a expose op. We'll make a new function for that so that we can have a different case expression. And here we'll do okay, and then while loop. Honestly, we'll just do it like this, condition. We don't have to always have them named. Body. Okay, so now we need a function expose op, which is going to take operator, which is going to be l.primop. Is that right? Yep. And it's going to return an la.primop. And I think that here's another possibility that we can introduce a panic, in that we should not get to this one. So we should not have an unwrapped vector. Okay, so let's match over that. So this is, these are going to be easy. Let's put this one at the top. We'll say panic as unwrapped or untagged vector construction. Okay, and then the rest of them are fine. We can do and expose expert A. And again, this is going to be very mechanical. The one thing that we should be doing here is this should import EOC Lang's ltup comp, because we want to reuse that. This is not something we want to redefine. Then we don't have to type. Then we don't have to redefine that, so we don't have to be translating this dumb little enum over and over and over. We did this previously as well. So again, mechanical stuff. Okay. This is basically the same, except it's minus. Negate. This is or. This is plus. It's interesting to me, in a lot of these transformations, a lot of it is mechanical because a lot of the semantics translate to the next layer. But there are cases like this panic here that says, oops, we didn't type check this correctly. We didn't wrap the types around the vector. And so you have a combination of, oh, I have new semantics, but I also, because we've got these new expressions, but we've also got expressions that are removed. Like we're removing this vector operator, and we're replacing it with the bits that call to the garbage collector. Okay. Okay, this needs to be LA.vectorref. Okay, so there our primitive operators are done. And now we can go back and think about what we do here. So this is a thing that, you know, we in some other passes like uniquify, we make sure that variables are unique. I'm not sure if uniquify will come before expose allocation. That would be interesting. I think it probably will. In fact, let's have a quick look. They usually do the diagram at the end of the chapter, so let's see if they do that. Yeah. Okay, so shrink, uniquify, expose allocation. So we can be sure that all the variables have unique suffixes on them now. And so we should be generating some of our own temporary variables for these things. We're going to need okay. Yeah, this is the path we're going at. Okay, we're in 6.3. So we need to generate some nested lets. So I think, and then ultimately, this is the inner part, right? Okay, so we need, let's generate this. This is kind of almost like a template. We're going to need some helper bits there. So we're going to need to be able to determine the size of how many bytes we need to allocate. And I think that because all of our things are word aligned, we are going to just say 8 times length plus 1 of the elements. Okay, let's just do that. Okay, and that's how many bytes we need to allocate. Let's go ahead and say len equals list.length yes, and then we'll reuse it here. Okay, so then our inner bit we need to make a how should we do this? So like we need to bind all the variables. Yeah, let's say let's call it let fields is list.map expose expression of ES. Okay, so we have the fields, and we have generated all of the stuff that needs to be generated for that individual expression. For each of those elements. And then what we'll do is we will create a bunch of lets wrapping those in here. And it's one of the problems with this is it's not clear the nesting, but it looks like this, right, because like you want to make sure that this happens before you allocate, and then once this is allocated, this is bound to this variable. Like at the very end, you return. Okay, so let's draw it out. So we have a bunch of lets. First is going to be let fn equals expression n. All of those. And then we're going to have the GC phrase, which is a let do the GC potentially, let GC question mark, and that's bounded, an arbitrary fresh variable. We probably need something in here that'll keep track of how many we've generated. So we need, what I'm thinking about is like, how do we go from this set of expressions it's like I want to do it with just a fold of sorts, but the problem is that we have to inject into this spot, which is nested inside. So maybe what we do is we fold over the expressions, collecting like a map fold, right? We'll have it produce pairs of the variable name, right? And the transform expression. Yeah, okay, so and then there's the alloc, and then there's the let vector set business, and then finally we return the vector. We need a way to generate variable names that's safe. I think shadowing. Oof. This is a space where we don't have a global counter. I mean, let's look at what we did in Uniquify. I think, yeah, we were passing the counter in and returning it. We might need to do that again, which makes this a bit more complicated. But then we could be guaranteed we're generating unique ones. So let's just say this takes and it's going to return and pair dot first. So now we need to do all this business. Yeah, I think this is the best way. And this is really just about making sure that we don't generate any anything that would collide. You know, it's probably okay in a lot of cases, but I want to be a little bit paranoid here. So this, we need to figure out what the fold is. The fold is it takes counter. And this is map fold, or fold map fold. Okay. And this will be, what does map fold take? It takes a function that takes the counter and the expression. What is it supposed to return? The new counter and the expression. So it's just expose expr EC. Okay, so I need to swap these. There we go. That fixes it. There's a question in my mind about whether I should put the counter into that as the first argument, and then I don't have to have this wrapper, but whatever. Okay. That's fine. We'll do... and we're just threading that through. It's funny, if that were actually not transposed, we could use fold over a list of these things, but map fold rather. Okay, and again, we've got to do all this business. This is okay. I am fine with the way that this is proceeding. Dog in the fire. Okay, so we need we need a binding here. And this is just op C1. And you know, again, we'll need, we're gonna have to put the counter int in here, and we'll go fix this in a minute. Really, it's just so that we can generate new variables that are guaranteed not to collide. We can name them whatever we want. So we'll have something like what Uniquify does with give me a variable that has this name in it. Yeah. And then we'll return that, C1. And this makes some of our stuff less, you know, less elegant. That's okay. And this will be condition body C2. Okay, so I think that's all of the expressions. Of course, this, let's comment this out and say to do for now. We'll get back to that. And then we need to do the same down here. So this is fine to panic. Wish there were a straightforward transformation I can do on this, but we can do some simple ones, like this doesn't introduce any new variables, neither does this. In fact, I'm going to move those up at the top. Okay. Monads. And I think for all the binary operations, we can reformulate them like so, and it'll be straightforward. Here. So yeah, let's just do this. Okay, let's go ahead and do the other binary operations. Or Okay. And then this will be the same for the other unary operation, except this will be la.not. Okay. And similar here. And for consistency, let's name it the same thing. Okay. This is another binary operator, basically. Has 3 arguments. Except this is going to be v, and this is going to be index, and this is going to be vector ref. It doesn't actually matter what those variables are named, I just want it to be as clear as possible. Okay. Value C2. And then we return C3, and this is vector set v index value. Okay, expose, so that takes counter. And those are also places where it takes counter. I guess I must have copied that. This is A, for whatever reason. Might go back and make those consistent at some point, but okay. So now we have threaded through we need pair swap there. Okay, we threaded through the counter. So now let's do so we got about 10 minutes left. Let's try to finish up this code generation. So what I want to do is I want to generate a fresh variable for each of those expressions in the vector. So we're going to have a kind of map fold. And what I want to return is a pair of that variable and the nested expression. And that'll be in a list, and we'll also return the new counter. So we're going to do that. And then we'll have a bunch of lets, and there'll be a hole in it. And that hole will contain these lets, and then this will have a hole in it, in which will fill with each of these generated variables with a vector set. We also need to generate a variable for that. Okay, so let me put down here, let's just make a function, fresh variable, and we'll give it a name as a string, and the counter is an int, and this is going to return a string and an int. So this is, we've done this before in some other places. I don't remember remember where. Do we do it in here? Yeah, new var. We could what do they do in their example? So they're saying like it's interesting for this one. Like this is the it maybe what we need to do is not generate if it's a literal, right? So maybe we make a I mean, we're going to need something like that, right? Or there was one where we like we were generating labels and we took the prefix. Something like that. We call it prefix. So this is going to be prefix. Let's put an underscore in there just for giggles. Int toString counter, and then return counter +1. Okay. Yes, it thinks it's unused. That's fine. So this we can use to create a new variable. The thing is, like, if an expression is an immediate, like a bool, an int, a variable, we don't need to generate a fresh variable for it. But if it's anything else, we do. Including, here's the interesting thing, including things like read or anything else that would create a side effect, because that needs to be sequenced correctly, and we could potentially, if we did this wrong, take that out of sequence. So I think what I want is it's interesting they do this with lets and not begin. Like vector set always. Maybe it has to do with the sequencing of garbage collection. Vector set always returns void. There's no reason to let bind it. I think with the numberings here, they're trying to show how these variables were generated. I don't see an _1 or something with a 1 prefix or suffix on it anywhere. And let's make our fresh variable just add that without the, because then we can do fresh var underscore and pass counter. But I see _3. I see 2 on this alloc here. I don't see a 1 anywhere. But if you that leads me to believe that they did alloc 2 was first thing, which I guess makes sense. You need to create a fresh variable. To contain the variable, or to contain the vector that you're constructing. And then that's passed into this and all of the things that are elements of the vector. Okay, and this _3 is what's generated next. We can take this approach. So we go, again, this is recursive. So we're always going into all of these first. Like you do expose expression on each of these things. But let's assume we're just saying vector 42, which would be everything here. So this is, we create a thing which is the allocation, alloc2, and we know the length of the elements, which is 1. But we're going to start from alloc2 and work our way backwards through the elements of the vectors, wrapping this let vector set around those. So we'll do a fold right on that. And then we wrap that with the let alloc. We wrap that with the called a garbage collection, and then we're done for each of these. So but we're not done if there are any we're not done if there are any variables. So we need, while we're going through, because I mean, this is a little tiny optimization. We could bind up here or something to 42 and just, that would be the easy way. There's a bit of inlining here that's implicit in their example that I don't know is necessary. So if we assume that this is just a mistake and they're like, you should always bind everything, then this would actually be, we'd have a let around this, which binds this variable, binds this value to a variable. Okay. So let's go ahead and let's get the we've got to go down into these expressions at the very least. So what I want to get out of this is let's do we'll call it alloc is fresh var alloc counter, and this is going to be, so we'll create that one first just to follow their example. Okay, and then we need to I think that we can bind, or we can figure out what the length is already. We can say list.length of ES, and we can let size, or they were calling it bytes up here. Call it bytes. Length times 8. Okay. And then we can fill in those bits. And that's length plus 1 times 8, because we need the tag. Oh, sorry, Gleam. You want brackets, not parentheses. Okay. Okay, so our expressions, we're going to say C2 because this is going to be a map fold again. These are we're going to go into the nested expressions. Is there a map fold R? I guess it doesn't really matter. Okay. So we need to do so this is going to be mapping over ES, where the accumulator is going to be the counter. Yeah. Okay, and then our function is going to take, we'll just call it the counter and the expression. And what we want to do here is we want to call expose expression on, right? And then we're going to return the updated counter. This needs to return int and whatever type. So, and then we're going to have a pair of, let's of the variable and the updated expression. Okay, so it's just complaining about it here too. I want to make sure that these are, yeah, okay, so it's just saying it's not used. And this is a list of, here's the variable binding and here's the expression. That's what I wanted to get to, because what we want to do now is we'll say I want to make this portion first, So we know that here's the alloc variable. That's what's going to be returned. So let's go, let's call this a set fields, right? Is going to be fold right. Not that it matters, but it just feels good to do this backwards to forward. We're going to fold right over expressions, and we're going to start with the variable of alloc. So that's going to be the contained expression. And fold right takes this is the accumulator expression. This is a variable and an expression. So we're going to do, we'll call it accumulator. And this is var, and we're going to ignore, well, let's just say, we'll call it p for pair. I'll call it var xp for variable and expression. We're going to do, so here's another problem, is that we need the counter, because we're going to generate fresh variables in here with these lets. We can't just let bind. I mean, we can, vector set returns void, but based on this transformation, we need to be generating fresh variables. Okay, so I'm going to say let ignore is a fresh variable of, so we have underscore, right, and accumulator is a pair of expression and integer. Okay, and then we're going to generate this vector set. But there's an additional problem in that we need to know where we are to know which field to set. Okay, so we'll do length. Length -1. Okay, so we generate a fresh variable. We're going to say this vector set is, we're going to say vector set. So this is going to be la.prim vector set. Okay, we'll say nested is accumulator.0, and let field is accumulator.2. So let's do it like that. So this is actually the fresh variable returns a new count. Okay, so we're going to set okay, so vector set takes 3 arguments: index, expression, so the vector, index, value. Okay, so the expression is var of alloc, right? So we're setting that. No, it's v, not. v index value. Okay, so we're setting v, index is field, except that's la.int of field. And then value is going to be so this has a type of string and expression. So I'm going to say la.var. Okay, so there's our inner bit on this let. And I think I want to go until we finish this algorithm. We're not that far out. It feels rough, right? But we're not that far out. Okay, so we have set the field in the vector. And then what we need to return here is this accumulator has the inner expression, the count of fresh variables, and the length of the vector. So what we want to return from here is a let binding, and we're going to use it's going to bind to what's going on there? What are we missing? Okay. So we want to return a let binding. We're going to let ignore a set, and then we'll include the nested, right? And then we have our new count, and then we want field -1. Okay, so that gets our let bindings on this last part. Okay, and then what we're going to do here is we'll have C3 and ignore the field. Okay, so we've iterated through all the fields, building up this lower bit. Now we wrap it with these. And then we will okay, so let's say okay, so we're going to say we need to generate this ignore. Okay, so we're going to generate a new... I know that function's not strictly necessary. It just feels good to make sure that we do that. We could implement that in every spot, but... And there's probably some refactors that we can do on this that'll clean things up. Okay, so we have we're creating a fresh variable for this. So far, so good. Okay, so let's generate that GC expression, which is going to be this bit. Okay, and I kind of need to, because that's a little bit intricate, I need to make sure that I can see that while I'm typing this. Okay, so this is going to be an if, and then okay, the condition is going to be less than and that's going to have a primitive expression plus global value, and we're running a space here. Okay, global value of free pointer Okay, so if we add 16 to the global value free pointer, getting a little dizzy with all these parens. That's fine. Okay, and then we want to compare that to global value from space end. Okay, and then if true, we say la.prim, la.void. Okay, otherwise we say collect bytes. Okay, so there's our GC statement, basically. If the amount of free space left, or rather, if when we add the size of the vector to the free pointer, we still have space, so it's less than the end, then do nothing, otherwise try to collect 16 bytes. Okay. So that's that bit. And then what we want to do is I'm going to call this GC alloc set. We're going to combine that with we're going to let our ignore variable be bound to GC, and the inner part of that is going to be another let of our alloc variable is going to be expression allocate and we're going to say length, right? And then we're going to use the type. Okay, and that's going to contain the set fields. Okay, so there's all of our wrapper for that. And now, finally, we're going to go through and zip up the variable names with their expressions. So, so we'll wrap this with all of the field bindings. Okay, and let's do, remember this needs to return an expression and a counter. But with mapfold, the accumulator comes first in both the return value. So maybe we can just do, let's do list.mapfold, fold map, mapfold. Interestingly, here, what we should do is we should import that and then not redefine it. Cool. Okay, then that's not an error. We don't have to build any translation goop. Okay, so list map fold. We're going to go over the expressions. Or maybe we just fold right. Yeah, fold right. So this takes a list. So we're going to take the expressions. This is a list of the bindings, right? And then we're going to give it the accumulator is going to be our internal, our GCAlex set, and then the last counter, which was C4. And this is going to have the, you know, the accumulator and the var expr. Okay, and what we want to return here is you know, this is not going to introduce any new variables, so this is just introducing bindings. So we can say la.let this is going to be var expr.0 is the variable, var expr.1 is the expression, and then accumulator. And then that will be what we return. Okay. I think we need to see what this looks like. So what I want to do is maybe we can do this in a test. Yeah, let's go ahead and write a test for this. I think that's the right way to do this. That's how we've been doing it in the past. So let's do expose allocation test. And we're going to do import EOC passes parse. And we need Glee unit should. Okay, and this is going to be l.program. So we're going to say input parse.tokens should be okay. Parse.parse. it's just complaining it isn't used. Okay, so let's do expose allocation test. And we're going to use their example up here. I don't think that we're going to produce the exact same thing as they do, but maybe what we can do is just have this echo the output of the pass. Okay, so this should also do. We need to type check the program. That'll get us what we want there. Okay, so we need, let's use their program. And then let's say P and then we'll make a failing assertion so that just fails. Okay, and I would love to be able to pretty print this stuff, but let's get it into here. Yeah, let's do that. Or no, let's do it inlalloc, and we'll say fun dummy, and then let's have it pretty print that so we can read it. Okay. That reminds me, at some point we'll do a side quest, which is to have a way for us, and this will go back into the compiler explorer thing that we did. We'll have a way for us to pretty print these syntax trees back into concrete text, which will be useful for visualizing each phase, and then we can make it in the Explorer that you could pick what phase do you want to stop at, and you can see the intermediate output. That would be really, really good. Okay, so what we want to look at is how close is it to this. So let's hide the Project Explorer and we can have a look at that. Okay, so we have a program. It has vector ref, vector ref. So far, so good. So then we have let, and here we did a wrapping that they did not. So we said F5, and maybe I want to rename that to field. And that contains the inner one. So at least we're getting _4 where we expect it on this one. Except we have alloc1. I don't know why they started at 2, but whatever. But you know, it's allocating one of a vector integer, so that looks right. It's binding _3 to vector set on this vector in field 0. Var f2. So this is where we bound var f2 to 42 up here. Okay, and then it's finally returning the allocated vector. Okay, so they got 6. we got 5, but this is like the order of allocations there. I don't know. That's weird. I don't know how they went through theirs. Okay. So we bound F2, and then down here we have another GC bit. So 16. We're expecting that's correct. Okay, and then we do alloc 0. That's why we're off by 1. But so that's interesting. We're actually getting the fresh variable for the vector, the outer vector first, which is fine. But we're getting the correct size on the allocate call, vector t of integer t. We have ignored underscore 6, vector set on the allocated variable field 0 f5. So this is the thing that we bound up here, which is this inner vector. And okay, returning that allocated vector, and then we're referencing n0 and 0. So this looks relatively correct to me. We have some differences which are interesting, which is maybe we should name these variables vec init. That's a little tweak we can do. Maybe we'll do that right now, and then we'll call it a day. So let me comment this out. But we're getting the correct values both for the field indexes and for how much to collect or allocate, and the global values. So that's looking correct to me. All right, let's make that little tweak, and we will that's interesting that should fail does not actually fail. All right. I think next time it'll be good to go through the C code that's in here. It was just useful to go ahead and do the transformation for expose allocation first. So okay, so we want to call this this field vec init, and will be f. What was the other bit that was significantly different? I think it was that this happens after the inner one. Yeah, the order there is not completely clear for me. It's like allocate this inner variable, or like do all of this, and then allocate the outer vector, or generate the variable for the outer vector, and then generate the variable names. That's kind of weird. Honestly, I don't think that there's a wrong way to do it. It's just that that variable naming exposes the order in which you generated fresh variables. Let's see what that looks like. The other thing is we could start from 1 rather than 0. Like, that's fine. So we're still allocating the variables Yeah, I think we could do a little refactor on this next time and say, like, if we are, like, we could choose whether to generate variables for these based on whether it is whether it is an immediate expression or not. It's just that we don't care about it at this phase. This is high level. We could do immediate expressions, or we make those atomic in the remove complex operands. So, yeah. All right. I think that this is a good place to stop. I will make a commit. And this is chapter 6.3, expose allocations. And we're going to have some mess in there, but we can clean that up next time. All right. Thank you so much for sticking around, and I'll see you next week.